Okay, on to the last part of the Regents. That would be part C. There are 20 questions in part C. They are also free response, short answer type questions. And on this particular Regents, I can't remember if it's like this on all Regences, but they're grouped into sets of 5, so 4 sets of 5 questions each. It's kind of nice because it allows us to be a little bit more in-depth with the questioning style. You get a couple different questions you can ask about different situations. The first one is one that I explicitly teach every year in our electric fields topic. This is essentially the Millikan oil drop experiment. We spent probably like 20 minutes going over this. There were some homework questions. I believe it comes up on the test. It's the first time I've seen it come up on the Regents, which means probably won't come up on the Regents for a while again, but I was very glad that I taught it. Diagram shows a negatively charged oil drop that is suspended motionless. That is key, suspended motionless, between two oppositely charged parallel horizontal metal plates. The electric field strength, sorry, get to the right page. The electric field strength between the charged plates is 4 times 10 to the 4th newtons per coulomb. That is capital E, electric field. The 1.96 times 10 to the negative 15th kilogram oil drop, that would be the mass, is being acted upon by a gravitational force Fg and an electric force Fe. So they're basically drawing a free body diagram for you, and that shows you why it is suspended motionless. You have two balanced forces. That's going to be key when we get to 68 and 69 through 70. 66 through 67 was probably the most shocking thing that I've seen on the test. I understand why the question is asked. I understand why the mistakes happened, but I was still shocked that so many people missed either one point or both points on 66, 67. This is a gimme. Calculate the magnitude of the gravitational force Fg acting on the oil drop. Show all work, blah, blah, blah. Okay? Gravitational force. Now, I don't know if just seeing the word gravitation made everyone think, oh, the big scary equation Fg equals g m1 m2 over r squared. But stop and think for a second. You have no information that would tell you otherwise that this is happening, let's say, off of Earth. So there's no reason to necessarily assume it's going to be anything like super hard. You could look up the size of Earth. You could also look up the idea that, or you could say, okay, likely this experiment is taking place near the surface of Earth, so you could use the radius of Earth as r in that equation. I'm going to write it here and then erase it in a minute. So I mean, you could use this, I suppose. Sorry, I forget. We do M1 and M2. You could use this, but it just seems really difficult. What's the other way to calculate the gravitational force? The force of gravity. The weight. Okay? All those words mean the same thing. The much easier way to do this is just Fg equals mg. And I was shocked at how many people I saw miss this. Okay? You're told the mass, you know little g. It should be very easy to find Fg. 1.96 times 10 to the negative 15th kilograms. Don't overthink it, guys. It's not as hard as it looks. You need to understand that the force of gravity is the same thing as the weight, is the same thing as the gravitational force. Those are 3 words, or 3 phrases that all mean the same thing. The answer to this is, let's see, 1.92 times 10 to the negative 14th newtons. Okay, very simple. Now 68, determine the magnitude of the upward electrical force. Okay, I did already say it, they were the same thing, but if you wanted to show the work, here's how you do it. Let's kind of copy over our free body diagram here. We've got Fe holding this up. We've got Fg pulling it down. This is our drop of oil, Xy. Our net force in the y direction is Fe minus Fg equals MAY. Sorry for squeezing it in there. Now, how do we know anything about the acceleration? Well, we're told that the oil drop is suspended motionless, okay? If it was motionless for an instant in time, then I wouldn't be able to say this, but if it's suspended motionless, it kind of implies it's staying motionless over a period of time. And if it's staying motionless, that means the velocity stays at 0, that means it's not accelerating. That means our acceleration is 0. And I'm led to this, Fe equals Fg. I just figured out what Fg is, therefore Fe must be the same thing, since my free body diagram and net force equation lead me to the fact that they are equal. 1.92 times 10 to the negative 14th newtons is Fe. 69 and 70, calculate the net electric charge on the oil drop in coulombs. I saw someone convert this to elementary charges. They had it in coulombs, they converted it. It drove me nuts. In coulombs, that is the key here. Or no, they had it in coulombs, they converted to elementary charges. It was awful. So, we know the electrostatic force. We're looking for the charge. Well, it turns out that we do have an equation for this. The electric field is equal to the electrostatic force divided by the charge. And that's because the electric field, it's kind of like, it's along the same lines of why we use it as the reason we use voltage. We talk about voltage or potential difference because we want to know about the energy use per charge, the energy that is given to each charge. We talk about electric field because we want to know the force per charge, okay? If something has a big charge, it's going to get a big force on it. We want to know about the ratio of the force to the charge. We want to find Q, we know E, and we know Fe. At that point, it just becomes a standard plug-in equation. 4 times 10 to the 4th newtons per coulomb equals 1.92 times 10 to the negative 14th newtons over the charge. We solve for the charge by multiplying both sides by Q, dividing this over to the other side. We get that Q is equal to 4.80 times 10 to the negative 19 coulombs. Now, if you're really smart, you would know that the charge, you would know that would be 3 electrons. If you think about it, really, this should be negative because it's a negative, it even tells you negatively charged oil drop. The question really should say the magnitude of the net electric charge, but it didn't. But keep in mind, really, this should be negative, okay? I don't think we took any points off if someone made it positive because it was already told to us in the problem that this was a negative oil drop, okay? There's the first part of, there's the first set of questions down. Let's move on to 71 through 75. Okay, this is another electricity question. All right, in a circuit, a 100 ohm resistor and a 200 ohm resistor are connected in parallel to a 10 volt battery. So off the bat, I'm just going to draw a picture of this. Okay, that usually helps. 10 volt battery. Here's my 100 ohm resistor. If you ever forget the symbols, they're all in the reference table, remember? There's a 200 ohm resistor. First thing we need to do is calculate the equivalent resistance of the circuit. It is a parallel circuit, therefore the equation is the kind of weird one. 1 over Req equals 1 over R1 plus 1 over R2. We're looking for Req. So 1 over Req equals 1 over 100 ohms plus 1 over 200 ohms. We end up, and you can do this a number of ways. You could turn these into decimals right now, add them together, take the reciprocal. You could do some sort of weird cross multiplication, or finding the least, the least common denominator. I won't go through the math, but you need to make sure that you get to an answer of the equivalent resistance is equal to, let's see, where is it on here? Gotta flip my page. 66.7. 66.7 ohms. Okay, that is the equivalent resistance here. All right, there are probably other ways to do it, but that's one that in general is one way. That's probably the easiest way to do it. 73 through 74, calculate the current in the 200 ohm resistor. We have to remember another fact about parallel circuits. The voltage drop at each resistor in a parallel circuit is equal to the voltage gain of the battery, meaning this resistor has a 10 volt drop associated with it, and so does this one. Okay, that's different from a series circuit, where the sum of all the voltage drops has to equal the voltage gain of the battery. So, current in the 200 ohm resistor, we go to Ohm's law. Ohm's law is V equals IR. We know that the 200 ohm resistor must have a voltage drop of 10 volts. We're looking for the current through it. We know the resistance of that resistor is 200 ohms. when we solve for I believe we get 0.05 amps. Okay, that is how much current is going through the 200 ohm resistor. And we could check this in a number of ways. We could figure out the current going through the 100 ohm resistor, add those currents together and see and use Ohm's law to see if we get the right REQ. The nice thing about circuits is you can check your work a number of ways and it will tell you if you're right or not. But we'll move on. 75, determine the power dissipated by the 100 ohm resistor. Now, you might want to say, oh, power, that is the voltage times the current. That's the first equation in the reference tables. But think about it. You don't know the current in the 100 ohm resistor. You would have to calculate that. And what if you calculate it wrong? You're giving up that point. Okay? Instead, what you really should be doing is you really should say, what do I automatically know about this resistor? I know the resistance, and I just got done saying I also know the voltage drop is 10 volts. I'm going to stick to things that they are directly giving me. It's a smaller chance of messing up. So I know that one of the equations for power is V squared over R. I know that the voltage drop for that 100 ohm resistor is 10 volts. I square that. I know that the resistance is 100 ohms. Therefore, the power dissipated by that resistor is simply 1 watt. Okay, 1 watt. All right, there is another, we're halfway done with section C, and I'll finish up with one more video.